just giving us a very quick look at some elements of mechanics. I mean, we could fill a whole course with doing justice to mechanics, but just looking at some of the elements of it that are most important for the simulation of virtual environments, or typical scenarios in computer games and so on. So now we started this last time. So we're doing basic mechanics. So we're looking at position, velocity, and acceleration of objects, and we're using vector-valued functions in general to track objects through 3 dimensions or 2 dimensions. We'd be using vector-valued functions for these. And the same, so we have a vector-valued function, r of t for the position of something, v for its velocity, and a for its acceleration. These are still vector quantities, and they hold the same relation to each other through the time derivative. So velocity is the derivative of position, and acceleration is the derivative of velocity. Now there's no problem with differentiating vector-valued functions. You can differentiate a vector-valued function here, like here's the position r, and it's got 3 component functions, an x, a y, and a z component function. Well, to differentiate r in order to obtain the velocity, you just differentiate each component in turn. Okay, so you just perform the differentiation component-wise, and that gives you the vector for the velocity. Now so still just quickly reviewing last time, the most common setting of looking at things is in constant acceleration. Okay, where there's a constant acceleration at work on the object, or a constant force at work on the object. And we looked at a couple of problems related to that. And then we came on to, so this is where we more or less ended last time, introducing this idea of approximations. So in order to save time, because performing a full mechanical simulation of all the physics in an environment is going to be computationally expensive. So if you want to cut down on that, for 2 things. In order to speed the simulation up so that you can simulate it in real time. So it's not taking 10 seconds to simulate an animation which is only going to last 5 seconds. Then the computer can't keep up with producing the animation in real time. So you want to use approximations to cut down the amount of computations to enable you to do it in real time, and to just be able to do it on lower powered computer processors, but also to be able to admit more objects into the simulation. Okay, so if you can cut down on the computational complexity, then you'll be able to simulate more objects in the scene and provide a richer, more realistic experience with more objects flying around the scene and so on. Okay. Now there are two types of approximation model we're going to look at here. One is the constant velocity model, and one is the constant acceleration model. So in reality, as your object is flying through the scene, its velocity and its acceleration might be constantly changing, perhaps, due to influences from various forces, or due to collisions, or due to user input, various things happening. Now, the simulation, remember, works by simulating, it has these small time intervals between each frame of the animation. So this is called a bound. And it has all the information of where everything is at the start of the bound, and then it does the simulation and works out where all the objects should be at the end of the bound, and then it draws them, produces that next frame of the animation, and then just repeats that process. So the thing is, how does it simulate the objects over the course of a bound? So the bound is some small fraction of a second. How does it simulate what's happening with them, simulate the mechanics over the course of that bound? Well, there's 2 kinds of approximation. So a rough approximation would be to assume that everything is moving with constant velocity over the course of that bound. Okay, so whatever its initial velocity is at the start of the bound, it's going to continue to move with that velocity over the course of the bound, and so end up, so it'll move in a straight line. Constant velocity means you're moving in a straight line at a certain speed. And so it'll be wherever it is at the end of the bound, just that small distance along that line. So that assumes that the velocity is fixed over the course of the bound. But that mightn't be that realistic, okay? Because if the object is moving in, say, a gravitational field or whatever, it won't be moving in a straight line. It'll be moving along some curved path. So a more realistic approximation would be to assume that so we would allow the velocity to alter over the course of the bound, but what we keep constant is the acceleration. So we assume that from the beginning of the bound to the end of the bound, the acceleration is held constant at whatever value it had at the start of the bound. Okay. But we would modify the velocity over the course of the bound according to that. Okay. So it should be that the constant velocity model would provide, providing the bound step is small, it should provide a reasonable approximation to the actual full-blown physical model, mechanical model. But the constant acceleration model should provide a better approximation still. Okay, so we'd maybe like to investigate that now, and try and see if we can see or appreciate, maybe using a bit of calculation on the computer, to compare the performance of both models with the full-blown simulation. Okay. So what's going to happen in the constant velocity model? How might the nuts and bolts of the calculation of that model be carried out? Well, okay, so I've given a little bit of a description here, but it's kind of more or less contained in the things we've talked about up to now. So we have the bound delta t. We've got n objects in the scene, say, objects indexed by j, from j equals 1 up to n. So over the course of the bound, each of those objects will undergo a certain displacement sj. So the jth object will undergo a displacement sj. So sj will be its displacement vector over the course of the bound. So this small vector which indicates its starting position and its end position, or it's the vector joining those two. And that will simply be whatever its velocity is at the start of the bound multiplied by the time length of the bound. Okay, so we're considering that the object is moving with constant velocity. So it's moving in the direction of the velocity vector. So we're just simply multiplying that by delta t, and that indicates how far it's going. So if we have rj, if qj represents the initial positions of these objects at the beginning of the bound, if the object j begins at qj, at the end of the bound it will be at rj, and rj will just simply be its initial position plus the displacement it undergoes over the course of the bound, and that gives you the new position rj, the updated position of the object. Now we will have to update, to prepare the calculation for the next bound, we'll have to update the velocity to whatever its new value should be for the beginning of the next bound. So, or whether you do this before or after, so in each bound calculation, you'll have to update the velocity, okay? So if uj here is the old value of the velocity, then you obtain the new value of the velocity by calling upon whatever acceleration is supposed to be at play and multiplying that by the bound length delta t as well. Okay, so let's just look at a quick exercise which asks us to model one step of that. Okay, so that's this exercise 8.4. So let's look at this document camera. Button press. I'll just switch it off. Okay, so here we'll consider a rocket moving under its own power in a gravitational field. So there's two things giving acceleration to the rocket. its own motor and the force of gravity. So we'll assume that the motor is giving it a horizontal acceleration of 1 meter per second, and that the gravitational field, as usual, provides a acceleration in the vertical direction of minus 9.81 meters per second. So that's an acceleration downwards. We assume that this vector here is the initial velocity vector, and initially it's at position given there 0.51. And using a bound length of a tenth of a second, what would the position be at the end of the bound? Okay. So the kind of what's going on here in the language of what we've introduced is that we have an initial position u for this of 210 is given there. The acceleration that's at work is the vector 1 minus 9.810. So that acceleration vector sums together the two contributions to the acceleration, the one from the motor and the minus 9.81 from the gravity. Sorry, use the initial velocity. Sorry, that's. And Q, the initial position, is given as 0.51. Okay, so we could update the velocity. So how would the velocity get updated? The velocity will get updated to the new value v of the velocity will be the old value plus the acceleration times delta t. So this will be the vector 210 plus the acceleration vector 1 minus 9.810 times the time-bound value delta t, which is a tenth of a second. Okay, and if you just multiply through by the scalar 0, 1 and add the two vectors together, you're going to get this kind of value, 2.1, 0.019, and a 0. Okay, so this is the updated velocity vector. So for the next time bound, then the displacement would be the displacement you undergo would just be s, which is should be the velocity at play multiplied by delta t. So this will be this 2.1, 0.019 by 0 by the 0.1, which is the time bound. So the displacement here, the small movement that's happening to the object is 0, 0.21, 0.0019, 0. Sorry? Yeah, but that's there you're trying to take account of changing velocity over the course of the period. This first type of approximation doesn't try to achieve that. It just assumes that the velocity is fixed over the course of the bound, and it doesn't try and do any fine work with it. over that course of the bound. Yeah. Okay, and then we could update the new position. Update the new position accordingly then. As R is equal to Q plus S. So that, you know, I mean, it's hard to appreciate just on paper and pen how this thing might perform over. I mean, it's not so interesting how it performs over one bound. It's more interesting how it performs over a whole long series of bounds. So I think we'll switch for the next calculation. I think we'll switch to the computer to try and get a good picture of that. So I'll just go back to the computer. Yeah. Okay. So as we said, a better approximation might be provided by the constant acceleration model. So here you're assuming that over the course of the bound, the acceleration is held fixed, but it is the velocity, we take account of the changing velocity. So this is more kind of what you were trying to propose there. So, I mean, what kind of things would be involved in modeling this? So we would need to have to know the initial velocity of the object at the start of the bound. V is going to denote the final velocity. A is going to denote the acceleration taking place during the bound. And that's what's thought to be held constant over the course of the bound. Okay. So the new velocity, the velocity at the end of the bound, will be the old velocity at the start of the bound plus t times the acceleration, as usual. But now what's different now is before we had the displacement is simply the velocity times the sorry, I should have all these all these t's should be delta t's, shouldn't they? They should all be, yeah, they should all be the time bound. Sorry about that. So the t in all of these should be the delta t. It's just the small increment in time. Sorry. So before we had the displacement was simply the velocity times delta t. But here you're taking in the quadratic term as well, which takes account of the acceleration that the velocity is undergoing, or that the object is undergoing, and so the change in its velocity that's undergoing over the course of the bound. So this is calling back to the Suvat equations, the equations we looked at last time for that relate position, velocity, and acceleration. And there's two ones here, two alternative ones you can use, one either based on the old velocity or one based on the new velocity. If you use the new velocity, then there's a negative correction to it using the acceleration. But if you're using the old velocity, then the correction to it is kind of positive based on the acceleration. So if you're using the old velocity to estimate the displacement, you're kind of underestimating its position in a way, because the velocity is going to be changing because it's accelerating. You need to add on an extra bit according to what the acceleration is. Whereas if you're using the new velocity to estimate the displacement, you're maybe over-egging it a bit, because it only reaches that new velocity at the end of the time bound. So you have this kind of a negative correction to pull back the displacement a little bit according to what the acceleration is. Okay. Well, there's a little exercise there, 8.5, just to apply that over the course of a single bound. But I think we should really go on to 8.7, because this is really what's interesting about it is how do these two models compare? How do they compare with the full-blown simulation of the physics, and which one is the better approximation? Now we expect the constant acceleration model to provide a better approximation than the constant velocity model. because it's taking account of more information. And just the basic principle that the more information you take account of, the more closer to reality you should be. So we're just going to describe a setup here, and then I'll switch to, I've got it open ready, I'll switch to Sage. I've got, got all the commands in there. I've prepared the example, and it will show us some plots showing the performance of the two models, and we'll be able to have a look at them. Okay. So what this is set up here is we're, say, considering a rocket. Now, considering it's in outer space somewhere, far away from any sources of gravitation. Okay. Yeah, you can never get completely away from gravity, but presume it's in intergalactic space between galaxies. So any gravitation it has is very, very weak, and we can safely ignore it for the purposes of this experiment. So it's a kind of situation where the ship is in motion, and it's going to fire its rocket to halt its motion and maybe reverse it. Okay, so we're just going to look. It's all the motion is just happening in one dimension. So the rocket's moving this way, say, from a certain observer's viewpoint. It's going to fire its rocket pointing that way, so it'll be giving it an acceleration back in the direction where it came from. So the kind of thing that's going to happen is the rocket's going to come along, it's going to fire its rocket for a while, it'll slow down, eventually it'll stop momentarily, and then it'll start moving back in the opposite direction. Okay. So we just provide the necessary data to set that up. So we'll assume initially that from time 0, it's at position x equals 0. This is its initial velocity, 5 meters per second. And the acceleration that's happening, so at time 0, it fires its rocket in the opposite direction, which is going to slow it down and eventually reverse it. So the acceleration that's happening is a negative acceleration from the rocket. Okay, we're thinking it's moving in the positive x direction, so the acceleration provided by the rocket is negative, so negative 4 meters per second per second. And moreover, it switches on the rocket, but it increases the thrust from it. So we're going to assume that the acceleration itself is going to be changing. So this isn't even a constant acceleration problem, it's a changing acceleration problem. And we're going to say the rate of change of acceleration is -8 meters per second per second per second. Okay, a rate of change of acceleration is going to be in units, meters, seconds to the -3. So what we want to do for this exercise is plot the position of the rocket over the time range 0 to 1.5, or over some time range. The moment where it reverses is between these two values anyway. So we'll do it using the full-blown mechanical simulation, and then we'll also do it under the two approximate models. The two approximate models are cheaper computationally. They're quicker for the computer to do, but they're not the true story. But let's see how the approximations perform. Okay, so I've got everything set up here. Increase the, not big enough for everyone. So I've done this in Sage, but you could do a very similar thing in Matlab. So I've just put in the initial values of everything here. So initial position 0. So this x0, v0 is just a label. It's just a 2-character variable name. This dA dt, so that's the rate of change of acceleration. It's just a 4-character variable name. It doesn't mean the derivative to the computer or anything. I'm just storing this value -8 in that variable. Initial position, initial velocity, initial acceleration, and dt is the time bound. So we'll set those values up. I want to define functions using t. So this var t command, that's like the sims t command in Matlab. So then I define, so this is setting up the full physical simulation. Okay, so the acceleration function Well, the acceleration function, you just integrate the rate of change of acceleration. So you're integrating the dA dt. So you're multiplying dA dt by t, and you're adding on the integration constant, but that integration constant will just be the initial value of the acceleration. So the acceleration function will be minus 8 times t plus whatever it was at the beginning, minus 4, wasn't it, the initial value? So that will be stored. That function a of t we'll have at our disposal. Then you get the velocity function by integrating the acceleration function. So I didn't get the computer to integrate it. I just integrated it in my head as I typed it. So when you integrate this constant times t, you get the constant times t squared over 2. The a0, actually, I'll just leave it. Well, yeah. So that's plus a0 there, isn't it? To integrate a0, the t typed in the value minus 4. Anyway. And then you have a constant of integration, but that's going to be the initial velocity. When t is equal to 0, it cuts out these two terms, and so you're just left with the initial velocity. I'll share this worksheet after the lecture, of course, as usual, so you'll be able to just click the link and get to this. And then you get the position function by integrating the velocity function. Okay? Remember, you always had this relationship. You go down the screen by integrating. You integrate acceleration, you get velocity. You integrate velocity, you get position. Or you go up the screen by differentiation. You always have these relationships between acceleration, velocity, and position. So the position of the spaceship is moving just in one dimension. Its position x of t will be the integral of the velocity. So you integrate each of these terms. Just to make it more meaningful, I'll replace the minus 4 with plus a0 there. That would be. Integrate v naught, you get v naught t, and then finally you get a constant of integration, but that's just going to be the initial position. Okay, because when t is 0 here, chops out all those terms, and you should just have x of 0, okay, which is already defined for us. So we define those functions there. So you have to define acceleration first, and then velocity is the integral of that, and position is the integral of velocity. Just check, see what it's giving us. So x, it now has x as this function, sends the argument t to that polynomial, okay? And that's the kind of thing we expect. This cubic polynomial in t. When we're taking account of, so this 5 times t, that's a velocity term. The t squared term is a term due to whatever acceleration is going on. And the t cubed term is due to whatever change in acceleration is going on. Okay? So for changing acceleration, and velocity, we expect some kind of cubic polynomial. So let's see what that looks like. So we plot that. And so this is the graph of it. So the thing at time 0, the thing is moving in the positive x direction. So it is creeping along the positive x direction, and it proceeds maybe approximately or maybe exactly 2 meters. And then by the time it's traveled 2 meters, it's halted, it's stationary. And you can see its tangent is decreasing, so it's slowing down all the time until it's momentarily stationary, but then it starts to retreat again in the negative direction. And because the engine is still burning, it's getting faster and faster, it's getting steeper and steeper. But anyway, so that's for the purposes of the model, for the purposes of this experiment, that's the true situation. That's the full simulation of all the physics, taking account of all the accelerations and velocities and so on. And okay, now the computer produces the plot by just sampling it at, loads of closely spaced sample points, but we'll forget about that and just think of that as the true smooth curve of the position function. So but computationally that's maybe a little bit expensive because it has to evaluate a cubic polynomial. So there's a lot of multiplications involved in evaluating that function and working it out all the time. There'll be less calculations involved in carrying out one of the simulations. So now we're going to do the constant velocity simulation. So the way I've built this up, you could build it up a similar way in Matlab, is I just create a list of time steps. So these are going to be the individual time steps. They're each separated by a bound of 0.05. So what I've taken as times is this index I times 0.05 for every I in the range 1.5 divided by 0.05. So this quantity here is the number of time intervals of length 0.05 there are between 0 and 1.5. So that's them all there. So I have all these individual time values. So those time values, 0, 0.05, 0.1, 0.15, etc. They're all the time stamps of the frames of the animation, so to speak, or the frames of the simulation. Then I set up constant velocity positions. So this is going to be a list giving the positions of the object at each of these time stamps according to the constant velocity model. So I initialize it as an empty list, but I then append position 0. So because that's its position, the position of the object at time 0, according to the problem, is position 0. So the first element is 0. And then I'm going to develop this with a loop by just adding on the appropriate position each time until I get all the way up to the last time step. And I initialize the velocity. So the velocity is currently the initial velocity v0. And then we do this for loop. Now, the for loops in Sage and in Python, they look quite different to for loops in Matlab, but they work the same way. So what I'm doing here is for every time in times, now times is the list of times that we just looked at up there. So for every time in that, so for every element, and I've just, by saying time here, you're giving a name to the element of times. So for every time in times, I'm going to append to my array CV constant velocity positions. I'm going to add, so append means add an element on at the end. And it's going to be, now CV pos minus 1, that refers to the last element currently in the list. Not quite sure if Matlab does this, but I'd have to try it out, see if it does. But there's the kind of convention that if you index an array with a negative number, it means you count from the end of the array. Not if you index an array with a positive number, you count to the beginning and count into the array. But if you index it with a negative number, that means counting back from the end. So minus 1 indicates the last position in this array. So the new position we're appending on is the last position plus the velocity times dt. That's the constant velocity approximation. The displacement is simply whatever the velocity is times the time bound, and we just add that on to the old position, and that's the new position. So we add that onto CV positions, and then in preparation for the next run through, we update the velocity. So what velocity should the thing have at the next time period? Well, that's going to be whatever old velocity it had, plus whatever acceleration is at work at this time period. So remember, A is a function that I defined above. So A of a argument gives the acceleration at that time. So the velocity gets updated as the old velocity plus whatever the acceleration at work then is times the time bound. Okay, because that's the acceleration that's going to stick it to the new value. So we run that loop, and that goes through all those time positions, and we get an array of positions. So these are the positions for the object under the constant velocity model. So it starts at 0. Goes up a bit, it reaches a maximum value of what, 2.245 maybe, and then it starts to retreat, and eventually it's going in negative. So it seems to be doing similar behavior to our blue graph. And we'll graph this in a moment, and we'll be able to compare it with the true graph. So then I do exactly the same thing again, but now for the constant acceleration model. So I have CA positions. So I initialize my CA position array, stick a 0 in as the first element. So the for loop looks very similar for every time in the list of timestamps. But this time, the velocity, we update the velocity. So this updating here updates the velocity to its new value. And then I append on the new position as the old position plus the displacement. And so I'm using this form of the displacement expression where I'm using the new velocity. So it's the new velocity times the time bound, and then this negative correction due to the acceleration. So I have a negatively correcting it according to whatever the acceleration is times the square of the time bound. So that follows the equations in the notes there for the constant acceleration model. So you run that for loop, and then that appends on all these new positions to the constant acceleration positions list. It does a similar thing. It increases from 0, goes up to a maximum value somewhere of 2.1 something, 2.1 something, and then it turns around and it begins to retreat down to negative positions. So the same overall, similar overall behavior. But now we want to start plotting these things. So first of all, I set up my graphics object P to just be the original plot. So that was the original plot we've already looked at. Sage is really nice for building up multiple plots. So I say P is this plot. When I stick P, then it shows me what P is. Then I'm going to add something to P. And I'm going to add this. Now, what is this? This is, I'm adding a bunch of lines to P. And I'm adding a line between a set of vertices. But the vertices I'm using, the x-coordinate, or the horizontal coordinate, the t-coordinate is the timestamp, and the y-coordinate is the position under the constant velocity model. So this is going to give me a loaded lines joining these points of the positions under the constant velocity model. And I'm just going to color them green. So that's the blue, remember, is the true physics, so to speak, the true mechanics. And so you see under the constant velocity model, well, it's, pretty good approximation. But you see it's overestimating its position. It's thinking it's always thinking it's at a slightly larger x position. And that's to be expected because it's assuming that the velocity is held constant over each bound. But in fact, the velocity is decreasing, or the velocity is changing in the negative direction all the time because the rocket motor is constantly burning. So it's losing this information about the burning of the rocket over the course of each time bound. So that's why it's pretty good agreement at the beginning, but then it starts to overshoot. Okay, and the discrepancy will only grow as you run time on. Then we have a similar line where we're adding a bunch of lines between points. Of course, the fact that these things are straight lines, you can't really appreciate it because the time bounds are so close together. So the straight lines are so small, and their slopes are only changing very slightly. So you can't notice the piecewise linear aspect of the green curve. So let me add on the same thing, but for the constant acceleration positions. Though it looks a bit messy construction, but it's basically saying, draw me a bunch of lines between these vertices. So the x-coordinate, the horizontal coordinate is the timestamp, the vertical coordinate is the position under the constant acceleration model. And this index I just run I to every appropriate index, which is just go to however long the times array is. And this time I'm coloring them red so we can see them. Okay, so we get a better approximation. Blue, again, as remember, is the true mechanics. So the red is a much better approximation. It's, well, at this zoom level, at this resolution, it's kind of sticking with the original values for a lot longer. And then, okay, at this zoom level, we start to perceive a difference here. But the difference doesn't grow so much. You know, it's doing a much better job than the green curve of sticking to the true value. It's still overestimating it, because it's still, this time the red curve is assuming the acceleration is held constant over the course of each time band. But the way we set up the problem, the engine is delivering increasing thrust. So the acceleration itself is changing. So that's the information that the red curve is losing. It's losing the fact that the acceleration is itself increasing over, or increasing in magnitude over the course of a band. The red curve is assuming the acceleration is held constant over the course of the band. So that's the information it's losing. But again, that's kind of quite higher order information. It's not as bad to lose that information as it is to lose the information that the green curve is losing. Okay, so that's a better, rather than just doing the paper calculations over like a single time band, this is a better illustration of what these things mean and what's going on. So, but the good thing, so we kind of think it's a bad thing about the green curve that it's not correct. But the great thing about the green curve is it's much quicker to calculate, because you're only calculating to update the position. You're only just simply multiplying. So how do we calculate the green curve? The green curve was calculated back at this line. So it's just doing a single multiplication of two numbers and adding it to the old value. So that's, if you have to do that, 100,000 times for each frame of a simulation, that's not as bad as having to do this operation 100,000 times, say, for the course of a frame. Because here you've got to perform a multiplication here, then you also have to perform a squaring of the time band and perform another multiplication. So it's kind of, very roughly speaking, nearly twice the amount of calculations needed, individual computer processor calculations needed for the constant acceleration model. So the green one is a lot quicker to do. So you can perform the green simulation for many more objects and perform it in real time on much lower spec hardware, for instance. Okay? So those are the considerations that are in play when you're deciding kind of which model to use, or deciding to use one of these approximation models at all. Okay, we'll leave it there for the moment, and I'll see you in an hour